now we want to turn our attention to TE mole inside a rectangular resonator with a conducting boundary. And we follow very similar analysis and argument when we did for the TM mole inside a resonator. Now think about the TE10 waveguide mole in previous lectures. We have the mole field like this. Again, electric field will be along the surface normal direction, and the magnetic field on the surface is going to be tangential to the surface. And we want to cross down the structure by applying additional boundaries along z direction. So imagine that you cross down this waveguide with some boundary and create a box like this. And when you do this cross down process, you are going to establish standing wave along this z direction. Previously, we already have standing wave along the transverse direction, x and y. Now you have additional standing wave along z direction. And again, we write down the z component of the magnetic field and keep the sign plus and minus for this summation of the wave along z direction and minus z direction. And don't forget that we have a dispersion relationship like this. H squared comes from the eigenvalue of the Helmholtz equation, and you have this H squared equal to omega squared epsilon mu minus beta squared. And this H squared is given by the sum of this term, which is the k value along x and y direction. Now we want to decide this plus and minus sign by using the boundary conditions. Because we are talking about the z component of the magnetic field, and we knew that on the surface of the conducting boundary, the tangential component will be maximized for the magnetic field, and the normal component of the magnetic field will be minimized. Therefore, the normal component, which is the z component of the magnetic field on this surface and also on this surface, are going to be 0. So we specify a sign solution for this Hz along z direction. And if you put z equal to 0 into this sign, you don't have the normal component of the magnetic field on this side. And if you put z equal to d into the sign, you have psi p pi, so you don't have the normal component of the Hz field on the surface. So once we have this beta equal to p pi over d from this boundary condition, then we can start to look into all other field components. But be careful that when you set this sign solution for the H component of the field along z direction, you also know that this p cannot be equal to 0, because if you specify this p, this mole number, to be equal to 0, then this Hz also disappears. So the minimum value of p will start from 1. And you have the beta value equal to p pi over d, so you can put this into this dispersion relationship to calculate the resonant frequency of TEMMP mole, and p cannot be 0. So this is the expression for the resonant frequency of the TEMMP mole. And if you set this MMP not equal to 0, you're going to see that this expression is the same as the resonant frequency for TMMP mole. And we call those moles are degenerate because they have the same resonant frequency, but they can have different mole field. They can have T mole field or TM mole field, but their resonant frequencies are the same. And again, once you have the z component of magnetic field, then you can calculate all other fields. And you can also extract the physics from the expression For example, for this x component of the electric field, again, you want to have the tangential component of the electric field on the surface to be equal to 0 on those conducting boundaries. So you'll be expecting sign solutions along y direction and along z direction because the y surface and z surface will see this Ex component as a tangential field. And similarly, for the electric field along y direction, the y surface is the normal component, but the x surface and z surface are the tangential components. So you expect the sine solution along x and also sine solution along z, but cosine solution along y. And the tangential component of the magnetic field is the maximum on the conducting boundary. So you expect cosine solutions along y and along z because the hx component is the tangential components on y surface and on z surface. And similar physics you can find from the expression for the y component of the magnetic field. Now we want to look into the more numbers, and turn out that if you set n equal to 0 and m equal to 0 at the same time, everything goes to 0. So it turns out that you can set n equal to 0 and m not equal to 0, or m equal to 0, n not equal to 0. But you cannot set mn at the same time to be equal to 0. And so this is the rule for the TE mode inside this rectangular resonator. So let's look into the dominant mode for a rectangular box. And we derive the same expressions for the resonant frequencies for TE and TM mode. But the rules for specifying M and P are different. For example, when we discuss TM mode, we said that M cannot be 0, N cannot be 0, but P can be 0. On the other hand, in this session, we said that M and N cannot be 0 at the same time for a TE mode. So if you follow this rule, and also the P not equal to 0 for TE mode, then you can write down a possible dominant mode to be TM110, TE101, TE011. For example, for this TM110, it follows the rule that no M, neither M nor N can be 0. So the first two indices, the minimum number for the first two indices have to be 1, 1. But for P, it can be 0 for TM mode. So the last index can be 0. For this TE101 mode, we follow this rule. This M and N cannot be 0 at the same time. So you can write down this TE10 or TE01. But for the last index P, the lowest number is equal to 1. So you write down this 1 for this TE101, TE011 mode. So now we need to decide which one is the dominant mode by looking into the values of the resonant frequency. Whichever frequency has the lowest value will be the dominant mode for this resonator. For example, if we have the A larger than B larger than D, and D is the smallest dimension for this rectangular box. So this means that the D will give a big value in this calculation. So let's just take it out, just keep the A and B in this expression and specify this M and N equal to 1. So you have the resonant frequency of the 110 mode given by this expression, which is the minimum value of this resonant frequency. But to have the P equal to 0, it cannot be a TE mode. It has to be a TM mode. So the dominant mole for this rectangular box A larger than B larger than D is going to be the TM110 mole. On the other hand, if we have the A larger than D larger than B, B becomes the smallest value, so you want to take this out. So the smallest resonant frequency is going to be F101, because when you set this n equal to 0, you take out this the n over b. So you have this value to be the lowest value for the resonant frequency. Then you want to pick this TE101 mole to be the dominant mole, because when you specify this n equal to 0, it cannot be a Tm mole, because neither m nor n can be 0. So this is how you determine the dominant mole inside a rectangular structure. In the case of cubic structure A equal to B equal to D, then those three moles are degenerate. This means that their frequencies are the lowest, but their frequencies are the same. And we can also calculate the stored energy inside a rectangular resonator. For example, in this case, we choose the TE101 mole as the example. We can write down the expressions for the Euler field inside this resonator. And this field components are quite simple. You only have Y component electric field point upward and downward in this direction. And then you have the magnetic field around this x direction, and also the magnetic field line is going to cross upon themselves like this. So with the known mole field inside this box for the TE101 mole, then you can start to calculate the electric and magnetic energy stored inside this box. This first term is the magnetic energy stored inside this box for the x component of the magnetic field. And you have additional z component of the magnetic field, so that you add this term into the calculation. And you take 1/2 in front of it. This is time averaged results, because you do a time average over the oscillation field. You always appear 1/2 in front of the expression. And you can also calculate the electric energy inside this box. And this inside the integrant, this term is the energy density for the electric field. So you do an integration to get the total electric energy inside this box, and this integration over the volume. But still, you put 1/2 in front of it to account for the average time average value of the energy. Once you have these two, then you can sum them over. Turn out that the electric energy is equal to the magnetic energy, because for a wave, the electric energy and magnetic energy just oscillate, exchange for each other. And so you can just calculate this one or this one and multiply the solution by a factor 2. The final result is this expression. So once you have the stored energy inside this cavity, if you can calculate the power loss inside this cavity, then you can deduce the cavity Q. So the thing about the power loss inside a conducting wall resonator, well, basically the primary loss of the energy is the induced ohmic loss on the surface of a piezo conductor. And in lecture 12, we already calculate the loss density, the power loss density, which is the power loss per unit area given by this expression. This Js is the surface current induced on the surface, and this Rs is the surface impedance of this conducting material. And Js comes from the tangential component of the magnetic field. So if we know all the tangential component of the electric field inside the conducting boundary rectangular box, then we can calculate the power loss inside this rectangular structure. So for example, for this case, you look for the tangential component of the magnetic field that induced the surface current on this conducting wall. So for this TE101 mole, you have the two components of the magnetic field, one along x direction, the other along z direction. But for a rectangular box, there are 6 surfaces, and a pair of the surface is along x direction. Another pair of the surface is along y direction, and the third pair of the surfaces is along z direction. For example, for this z direction surface, there's one surface here, and there's the other surface is on the other side. So let's calculate the power loss on those surfaces one by one. For example, along z direction, you have the induced current on this surface, and this surface current is induced by the x component of the magnetic field. So you just plug in this expression into this integration over the surface, and you'll be able to get the power loss of the electromagnetic wave on this surface. Similarly, for the component, this SX surface, the relevant magnetic field is along z direction. So you put the z direction magnetic field into this expression, multiplying it with the surface impedance and integrate over this surface. Then you will be able to calculate the ohmic power loss on the surface. And the third component is the surface along y direction on the SY surface, on this surface. And both x component magnetic field and also z component magnetic field are tangential components with respect to this y surface. So in this calculation, you have two terms integrating over dx dy, which is the area on this y surface. But you have to multiply each term by a factor 2, because the say along the y direction you have a pair of surfaces. Along z direction you also have a pair of surfaces. Along x direction you also have 2 surfaces. So in front of each term you have a factor 2 in the calculation. And finally, you can come up with the total ohmic loss on the conducting wall of this rectangular cavity. So on the last page, we already have the expression for the stored energy, electromagnetic energy. Now we have the loss of the value from this calculation. Then you are in the position to calculate the cavity Q or resonant Q for this cavity. And on the first few pages of the first session, I told you already that this cavity Q is very important to interpret a resonator, including the how good this cavity can store electromagnetic energy, and also the filling time, decay time, and also bandwidth of this resonator. 所以呢，在第3节里头我介绍了有关于 TE-mole 在矩形的共振腔里头的分析。那算出来呢，它的这个 resonant frequency 呢跟 TM-mole 的这个公式一样，但是呢，它的 MMP 的规则呢不一样。也就是说，对于 TE-mole 来讲的话呢，这个 M 跟 N 不能同时等于0，所以这两个这个值呢必须很小心。你如果设定 M 等于0的时候呢 ，N 就不能等于0。那这个 P 呢最小值是1，对于 TM-mole 来讲的话呢，这个最小值呢是0。虽然它们公式是一样，但是这个 mole number 的这个规定不一样所以呢，这个我们在看 dominant mole 的时候呢，必须 follow 这个MMP 它的规定。譬如说，如果说我们只考虑 TE-mole 的话呢，那它的这个在当这个 B 是最小值的这个状况之下，那这个项贡献到这个频率最大， 所以呢把它给拿掉的话，你设定 n 等于0的话，那 n 不等于0了，所以呢你就必须设定是1。那这 p 的最小值是1，所以 Te101 mol 呢，对于这么一个结构的共振腔来讲的话，是它的 Te 的 dominant mol。另一方面，如果说这个 A 是最小值的话，你要把这一项拿掉来算它的这个 dominant mode frequency 的话，那你一旦设定 m 等于0的话呢，那这个 n 就不能等于0了。所以呢，在这个计算里头，你要特别的小心。那如果说 Te、Tm mode 一起考量的状况之下 ，A 大于 B、A 大于 D 的状况之下，这整个这个矩形的共振腔的dominant mole 呢会是 Tm110 mole。那在这个小节里头呢，我们得到这个TEMMP 的这个resonant frequency 的公式跟 TMMP 是一样的。那所以在呢 MNP 都不等于0的状况之下呢，那它的这个mole frequency 呢是一样的。如果说 MNP 的值设定在这2个 mole 里头都是一样的话，那它的 resonant frequency 会变得一样。那我们说这些 mole frequency 呢，都一样的状况之下，那这个 TEMMP 跟 TMMP mole 呢是这个它们是degenerate 的一个情形。那另外呢，在我们最后的部分，就是这个小节最后的部分，我介绍了如何一步一步的把这个resonant Q 把它算出来。那基本上，你就是先算这个在里头储存的 electromagnetic energy， 然后呢，再求这个 conducting boundary 上头的 ohmic loss， 然后呢，你算它的 ratio 就可以找到这个cavity Q 的这个值。那这个是这个小节里头的几个重点。